Okay, second part for today. We can call this organizing our own location in the Hubble Flow. This is our location within the Milky Way. We've seen this before. We're sitting essentially here in one of the spiral arms of the Milky Way, approximately 8 kiloparsecs from the center, in a disk that is around 20 kiloparsec. Now, in spiral galaxies, we've hinted that, yeah, they rotate. We can try to infer this rotation rate around the center of our own Milky Way. And then we come to the conclusion that, indeed, if there were no more matter present than what we see in the visible parts of the Milky Way, we should rotate slower. And this is indicated by this figure up here, which again I took from one of the previous assignments in the course, the previous years, where you can see observational data here, and then some fits to the velocity. This is the rotation date state. And the velocity curve here, they have various components in them. So, for example, if we had only the bulge, it would be like this. And if we will only, did they include just a baryonic matter disk? So that's a disk of baryons, yeah? Then the rotation curve should be something like this. And typically we say roughly that, well, if it were only such a disk, the sun should rotate with about 160 kilometers per second. But we infer that it rotates with about 220 kilometers per second around the Milky Way center. And the way to explain that is to add a huge, then, halo around here. And we will give, of course, when we study Galactic Dynamics, we will do some simple examples of how we can exemplify this and calculate this sort of at least order of magnitude inference, right? And then if you do that, then yeah, you can fix such rotation curves fairly well, as, like I said, even done within an assignment in this course, right? Now, this can and it has been done for many other spiral galaxies than the Milky Way. And it's quite revealing how this seems to be always the case. That is, spiral galaxies, they always have rotation curves, which typically then what we say is that they don't go down like this at large distances. They're much more flatter than indicated otherwise. Now, typically, we can think about this. Think about Kepler's laws. That is that if, like for the rotation of the planets, right, like our own Earth around the Sun, in the solar system, almost all mass sits in the center. Yeah? And that's why you get, as further away from the center you go, the slower the rotation speed. Okay, again, it's a calculation we'll do next week, actually. A very simple calculation you can do. So if you think about this in the context of a spiral galaxy, then okay, as long as we're in here, then of course, yeah, we have some inference, right? But when we go further and further outside the visible disk, then we should see a declining curve in the inferred rotation rates. And then you might ask, yeah, but if there's no visible matter there, how can we measure it then? And there the famous 21 centimeter line comes to rescue much often, because while there aren't much luminous matter in that sense around, there are some neutral hydrogen clouds from which we can measure the Doppler shifts, yeah, and infer the rotation rates. And then we see that it's very, very seldom that we actually detect this case at all. So in one sense, we cannot say that we know when the matter around say a spiral galaxy in general actually stops. I mean, it has to stop somewhere, you know, you have to start to find the curve, the downward curve at somewhere, because even if we interpret this through a giant dark halo, they also have to go down at some point, right? But it's very seldom we actually measure this downward curve in spiral galaxies. So it's a reminder that the size of a spiral galaxy in that sense is not so well known empirically. Now, of course, if we define a spiral galaxy only with the portions that we see as we have died, then it's a different thing. Then we can just measure where the disk is. But also that is not so easy, as we will come to later. All right, here is then our location in our local group of galaxies, as I always sit in. And we have two gravitational centers in our local group. One is around the Milky Way here, and one is around Andromeda. And we're surrounded by all these dwarf galaxies, satellite galaxies that are in orbit around these two major gravitational centers in our local group of galaxies. And these dwarf galaxies, like I said, they're very likely the most common sort of galaxy in the universe, but very difficult to detect because they're, well, dwarf, very faint, so we can't detect them to very large distances. Now, here is a typical illustration. This is a list of the known dwarf spheroidals in the local group in the intro course I took in 2007, which was from the IMPERS research, and then we knew about like 9 of them. But then, of course, this is from a review article, as better and better detection methods go down, we can detect more and more ultra-faint dwarfs, and then this can actually shoot up quite significant. So now we know of much more dwarf galaxies that surround our Milky Way and our Andromeda than were previously known. Even so, it's still not really enough. And that leads us to what we call the missing satellite problem of the major model for structure growth and cosmology that we have, the so-called lambda CDM model, from which these type of structures and galaxies are formed. And they predict that around a gravitational center like the Milky Way, there should be perhaps hundreds of these dwarf galaxies, and we don't see them. And the question is that just a detection problem, as sort of is hinted from the curve there, or is there still an issue there with the basic model? And that's to be further discussed during the course. Here's an illustration why it's challenging. This is like the Formax dwarf galaxy. And you can sort of infer already from this that, okay, here we can see the dwarf galaxy, but if you go even fainter, right, even this, which is a nearby dwarf, we would at some point not be able to detect it versus the background sky. And you have to have very sensitive instruments, and more sensitive, then you can detect more and more. But there is a limit here. So if there were a dwarf galaxy with even lower luminosity, then yeah, we would miss it in this survey. Now, we also move then within the larger framework, and from the cosmic micron background radiation, again, when you actually took, this is the COBE map, the famous COBE observations, and that's actually how it comes out. And that's not the, so to say, detailed small-scale structures and very homogeneous that we see. This is more of a dipole, and that's because the Earth is moving roughly 600 kilometers per second toward a direction which sits in the constellation of Leo. And you can infer that from the typical temperature and just applying the Doppler shift, as we have learned. Yeah. Now, we typically interpret that in terms of that there is a large gravitational center, a great attractor around that region. I should say that it's not so easy to infer as that there is like a big gravitational attraction sitting here, and then we're moving toward space, toward this large gravitational attractor. It's a little bit more challenging to specify what this is in practice. But we are moving through space, 600 kilometers toward this constellation. Huh? So there is a gravitational center there, a local one. So if we put this down, we typically call this a peculiar velocity. That is that the Earth's orbit around the Sun is on the order of 30. Then we have the Sun's orbit around the Milky Way center, galaxies motion toward the Virgo cluster, and the Virgo motion toward the Hydra supercluster. And we have to account for that when we want to do studies of, say, as we come to in the next, if we want to study the large flow within the context of Hubble's expansion law. Once we correct for these, for example, then the corrected cosmic microwave background radiation provides a very nice cosmic framework against which velocities then can be measured in sort of an absolute sense there, with very, very small temperature fluctuations, as we already know. But these are also key because those are the ones that we use in order to learn about the characteristics of this structure formation growth that I have referred to, that then builds all the galaxies. Now, here is this. This is the original Hubble diagram, and again, this is more for the intro course in astronomy, so I'm not actually going through this to some detail here, only that I will mention, you see the Hubble law here to the right, expressed right, that there are a few points I want to make for this course specifically, and that is that, well, I already said that in order to infer this, typically you need to correct first for the peculiar velocity. Yeah, and then this local Hubble law with the H0 is only valid for our nearby universe. Now, on the larger scales, as we'll see, the H, the Hubble parameter, actually changes with time. And that's where the cosmological model actually comes into play. Yeah? You need a cosmological model then in order to interpret your observations, the corresponding Hubble diagram, but at large distances. And that's also how you can constrain the parameters that go in to your cosmological models. Right? Now, here, this is the normalization constant, if we will, the Hubble constant, which is on the order of 70 kilometers per second per megaparsec. But there are uncertainties associated with this, and particularly there is a recent, well, relatively recent, and it doesn't seem to go away, problem which is called the Hubble tension. And that Hubble tension essentially means that depending on the method that you use to infer the values of the Hubble constant, whether it's the variable stars, the Cepheids in the local universe, or whether it's from the fluctuations of the cosmological microwave background radiation, you get typically quite different results. Not different in the sense that, well, they're 65 or 70, so you could say that's pretty good precision, but we have entered the era of precision cosmology now. And then they're away from each other with many sigmas uncertainty, actually. And this problem, perhaps it was believed for quite a big time to be measurement problems, because these measurements, these observations are very challenging. But more and more seem convinced too that this Hubble tension problem might actually be real. And that's another thing that we will touch upon in the later portions of the course. The differences in inferred values of the Hubble constant parameter. Now, like I said, on small scales, galaxies do not generally follow this Hubble flow, because their mutual gravitational attraction, I already mentioned that Milky Way and Andromeda, they're approaching each other, and they're on the course for a future collision, actually. So they don't follow mutual Hubble flow. And the local group of galaxies seem to move towards the so-called great attractor, and these velocities are then called peculiar velocities, and they need to take into account. Moreover, if we go to very large distances, the local Hubble law is no longer valid, and you need a cosmological model to get the h of t instead. Yeah? Then in these cosmological models, typically the assumptions you do is that on very large scales, distribution of matter is isotropic and homogeneous, and our location is not special. So in such cosmological models then, which again we will come to during later, typically there enters some parameters. These are these omega parameters here, where there is one parameter specifying the matter content of the universe, because the more matter we have, the more gravitation attraction we have. There is another parameter now that has entered, the lambda in the lambda CDM model, which is the Einstein's cosmological constant, normally interpreted as, or variants of it. And that's a repulsive force then. And this was actually reintroduced, we should say, into standard cosmological models because of a very famous experiment that was also experiments that were also awarded the Nobel Prize. Do we know what those were? Observations of what? White dwarf supernova, or type 1a supernova. Because these white dwarf or type 1a supernova, they are believed to be very good, so to say, standard candles. Okay, so it's essentially an accreting system whereby the accreting star then exceeds the Chandrasekhar mass, decreases from, say, binary star component or something like that, and when it exceeds the Chandrasekhar mass, it explodes. But since this is a very well-defined physics limit, it always explodes with the same intrinsic luminosity. That's what we call a standard candle. And then if you have the intrinsic luminosity, as we again know from radiative processes, and you can measure then the apparent magnitude, and you do some correction, and you have a sort of the extinction on the way, right? And that's where the calibration comes into play. Then you can get the distance. And then you can get distances, since these are so bright, the supernova shines brighter than a whole galaxy, you can do this on cosmological scales. You can get distances to cosmological scales. And when people did this in this supernova experiments, again, for the later, during the course, we'll go into details here, then they noticed that this did not fit into the cosmological models where you only took into account the matter component. You needed to add this repulsive force in order to accelerate the expansion of the universe. So that was the reintroduction. And nowadays there are also other indications why this has to be, again, from coming from a combination of sources actually nowadays, like the cosmic background radiation and the fluctuations thereof, particularly the baryonic oscillations, but also actually from these clusters of galaxy where we can get a good handle on the total mass, and that mass doesn't seem to add up to the total energy content that should be around, let's just say, for a flat universe, which is another observational indications that we have. But then again, with this has also come then that we have introduced, in order to interpret the cosmological observations, we have introduced additional components of dark matter, and they come from many different, and that will be a big portion of the course. You know, we have mentioned the spiral galaxies already, but they also come from the galaxy clusters, they come from the dwarf spheroidal, they come from the measurements of the cosmic background radiation, etc., etc. Okay, and then we also have introduced this additional component, which often is popularized, called dark energy. That's the lambda in the lambda CDM, so to say. And when we put those into the equations, then we can reproduce the observations much more. But of course, it is important. I think everybody here is very well aware. We don't know what it is. We don't know what this dark matter component is. We don't know what this dark energy component is. We don't even know if it is really a constant or not, or if it changes as time goes by. But then the thing here that one normally do is that one sets up the Friedmann-Lemaitre equations and then make predictions from that. And here is again just a calculation of this scale factor that we'll come back to from, well, again, the take-home written exam of the course. So it will come back to us. All right, we take a very short break here again.